We conclude our exploration of Chapter 4 with probability by looking at Section 4.3, an additional conversation about complements and conditional probability, both concepts that we introduced earlier in this chapter. Here we extend the use of the multiplication rule to calculate probabilities that among several trials we get at least one of some specified event. So we're going to look at several examples of problems that ask us to find the probability of getting at least one of something. We also consider conditional probabilities, which we introduced earlier. Recall that these are probabilities of an event occurring when we have initial information that some other event has already occurred. Let's start with using the complement rule to compute the probability of at least one. When finding the probability of some event occurring at least one time, we should understand the following. At least one has the same meaning as one or more. Let me say that again. At least one means the same as one or more. The complement of getting at least one is that you get none. And that is a concept that makes sense, and yet so many people confuse this. The complement of getting at least one is the complement of getting one or more. And the only thing that's not covered in one or more is none or zero. So the complement of getting at least one of something is that you get none of that. Therefore, if we let A be the event of getting at least one of some event, then a complement is getting none of that event. Finding the probability of a complement will therefore be finding the probability that event A does not occur, as we saw earlier. Therefore, the probability of getting at least one of something is 1 minus the probability of getting none of that occurrence. The probability of at least one is equal to 1 minus the probability of none. Here's an example from manufacturing. A factory of the global manufacturing company was manufacturing products with a defect rate of 15%. And this is based on data from the Harvard Business Review. If a customer purchases 12 of those products, what is the probability of getting at least one that is effective? These 12 selections are therefore going to be considered 12 different trials, each selection being a trial. We have a defect rate of 15%, and we want to find the probability that among those 12 selections, at least one of them is defective. This is equivalent to finding the probability that exactly one is effective, adding that to the probability that exactly two are defective, adding that to the probability that exactly 3 are effective, and so on, finally adding that to the probability that all 12 are defective. Because remember, getting at least one that is effective is the same as getting one or more. So it could be anywhere from one defect to all 12 being defective. Well, that's a lot to add. So we're going to use the complement rule to get to the same result much, much faster. If we let A represent at least one of the 12 products is defective, then a complement is that none of them are defective, that all of them are good, right? No defects means all of them are good. So to find the probability that all items are good, we are going to use the multiplication rule. There's an 85% probability that the first selection is good, no defect. There's also an 85% probability that the second selection is good, and so on. So if we multiply the probability that all of these 12 selections are good, we will find that that probability is 0.142. So again, this number right here is the probability that all 12 of these selections have no defects. All 12 are good. The probability that we're being asked for, however, is that we get at least one defect. Well, the probability of getting at least one defect is 1 minus the probability that there are no defects. 1 minus the probability that all 12 are good. So 1 minus 0.142 will give us the desired probability, which is 0.858. Notice that while this was a little bit of work, it certainly beats finding the probability that exactly one product is defective, adding that to the probability that exactly 2 products are defective, and so on, until we get to the probability that all 12 products are defective. Here's how we summarize our calculation. For a group of 12 products, there is a 0.858 probability of getting at least one that is defective. As far as quality control goes, this actually is quite high. Out of 12 products, we don't want to have a very high probability that at least one of them is defective. And the interpretation is that this company should look at improving its process so that the defect rate is lowered. Now let's return to the concept of conditional probability, which we were introduced to in the last section. A conditional probability of an event is the probability obtained by considering the additional information that some other event has already occurred. The notation that we saw is that the probability of B given A, which we denote here, is the probability that event B will occur given that we know event A has already occurred. The conditional probability of B, given that A has already occurred, can be found by assuming that event A has occurred and then calculating the probability that event B will occur as a result. We already played around with this a little bit in the last section, but here we introduce a more formal approach for finding the probability of B given A. The probability of B given A can also be found by dividing the probability of A and B by the probability of just A. Notice that this is exactly the formula that we introduced in our last section, except with the probability of A being multiplied here on the left. Let's look at this example. Let's see if I can move this out of the way. Using the following table, and by the way, let's look at the table first before we pose the problem. So we have what's called a two-way table. Each row here has subjects who are known to use drugs in the first row, subjects that do not use drugs in the second row. So this is based on fact. Subjects that do use drugs versus subjects that do not use drugs. The columns, on the other hand, correspond to drug test results, which could or could not match reality. Here we have the positive test results for drugs and negative test results for drugs. Okay, so this is what the test indicates up here on the columns, and then over here on the rows, this is the actuality. This is what is true. So there are some cases where the drug test result matches reality. These are called either true positives or true negatives. If a person is a drug user and tests positive for drugs, that's a correct test result. That's a true positive result. If, on the other hand, a subject doesn't use drugs and has a negative test result, well, though that's also correct, right? We have these 480 negative test results that coincide with reality. These are correct results. These are called true negatives. But on occasion, test results do not represent correct information. For example, let's look at the people here, these 25. These are not drug users. In reality, they do not use drugs, and yet they yielded a positive test result. That is an incorrect result. These are called false positives. And then over here where my cursor is would be another set of incorrect results. These are people who do use drugs in reality. However, the drug test did not detect that, and we have a negative test results. These are called false negatives. All right, let's pose the question now. If one of the 555 test subjects is randomly selected, and this number 555 comes from adding all four of these numbers, 45 plus 5 plus 480 plus 25. So if one of these 555 test subjects is randomly selected, we need to find the probability that the subject had a positive test result, given that the subject actually uses drugs. So the given that portion of this question is what we know to be true. The subject actually does use drugs. If we know that to be the case, that means we're only really interested in the people in the first row that are known drug users. There's 50 total, right? We know that the subject who's chosen actually does use drugs. So it must be one of these 50 people in the first row. Of those 50 people then, how many would have a positive test result? 45 of them. So the probability of getting a positive test result, given that we already know the subject actually does use drugs, would be 45 out of 50. Part B of this question is, if one of the 555 test subjects is randomly selected, find the probability that the subject actually does use drugs, given that we know the person had a positive test result. So if we know the person had a positive test result, if that is known to us, then we're really only interested in this first column. If we know they have a positive test result, that's already happened, then we're only looking at these 70 people total. 45 plus 25 is 70. So of these 70 people with positive test results, then how many of them actually use drugs? 45. So that probability will be 45 out of 70. So here we have a summary of what I said verbally in the previous slide. For the first question, we were asked, what is the probability of obtaining a positive test result given that we already know the subject uses drugs? So in the denominator of our probability, we're going to count the total number of subjects who are known to be drug users, and that total was 50. In the numerator then, of those 50, how many are known to have test results? 45. So 45 out of 50 would give us a 0.9 probability. And now let's look at part B of this question. If we were looking at the probability of a subject using drugs and having a positive test result, so using the more formal approach, we would get the same answer. But I want to make a point here. Whether we are using our common sense by counting or we're using the more formal approach of using the formula, we should get the same result. And I have no preference for one or the other as far as students are concerned, but I do want to go through the two approaches because there will be a set of students who prefer the more common sense approach or intuitive approach, and others who are very formula dependent, and so we want to give you the two choices. The big difference is that by using the intuitive approach versus the formal approach, we're less likely to get errors, because anytime we are dependent on a formula, there is the opportunity for making some computational errors. The intuitive approach is based on understanding conditional probability, whereas the formula approach is more mechanical. Again, I have no preference. I like to use the intuitive approach because to me understanding is important, but for those students who are more formula driven, you do have that as an option as well. All right, let's look at part B of the problem, where we're finding the probability that a randomly selected subject is a drug user, given that we already know the person has tested positive. Well, the denominator, again, should include the total number of people who tested positive. And we saw that was the sum of the two numbers in the first column, which is 45 plus 25, and here we have that 70. So of those 70 people who tested positive, how many of them actually are drug users? 45. So the answer to the second question would have a probability of 0.643, which written in decimal form is different than what we obtained in Part A. So in Part A of this question, we were finding the probability of obtaining a test result given that we knew the subject uses drugs. That probability was 0.9. For the second problem, the probability that the subject uses drugs given that we know the person tested positive was a different result, 0.643. It was exactly the same two events, but in reverse order. In general, the probability of B given A does not necessarily mean the same as the probability of A given B. And this is a clear example where 0.9 was the result for one, 0.643 was the result for the other. So these two are not necessarily equal. What we know to be true is what we list second. That definitely impacts the probability of the other event, and so these are not necessarily interchangeable. On occasion they are equal, but in general they usually are not. This is what we refer to as the confusion of the inverse. So going through the intuitive approach, in my opinion, helps us to avoid the confusion of the inverse because we're talking about what is known, counting the total number of cases for what is known, and then of that smaller set, counting how many satisfy the event that you're finding the probability for.